L'Hopital's rule has two advantages. First, it's easier. Second, it is more universally applicable. We cannot use algebraic approaches for the limits that we're going to look at here, but we can use L'Hopital's rule. So don't forget, we have to check the hypothesis of the theorem. In other words, is it true that the limit of the numerator and the limit of the denominator both equal 0 or a type of infinity? In this case, they both equal 0, right? If you plug in 0 for x here, you get e to the 0, which is 1, and 1 minus 1 is 0. And you plug in 0 for x here, well, you get 0. So this is a required part. You have to write this out before applying L'Hopital's rule. But once we see that, we can say, L'Hopital says that the original limit equals the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom. So the derivative of the top is e to the 3x because the argument doesn't change. But don't forget the chain rule. So derivative of 3x is 3. And then the minus 1 turns into a minus 0, so we won't worry about that. And then the x turns into a 1. We no longer have an indeterminate 0 over 0. We now have, well, if we do direct substitution, we get e to the 0 times 3 over 1, and that's going to be 1 times 3 over 1, or just 3. As a quick note, you can always graph these functions, and it's always nice to take a look at the graph and see what this thing does when x gets close to 0, and you should see that it looks like this graph just goes through the point 0, 3. It doesn't actually, there's a hole there, but the limit does exist. The limit equals 3. Fantastic. All right, next problem. We'll take a look at the limit as x approaches infinity of the natural log of x, and ask the question, is that the same thing as the limit as x approaches infinity of x? And the answer is yes, they both equal infinity. One thing we want to remember here is that natural log of infinity equals infinity. We know this because we are familiar with the graph natural log of x. It looks like this, and it grows forever without bound. Okay? If you're not sure whether there's a horizontal asymptote, go back to the idea of exponentials and see if there's a vertical asymptote. And since we know that exponential graphs don't have a vertical asymptote, we know that logarithmic graphs don't have a horizontal asymptote. Therefore, this thing is going to grow without bound, and that means that we do have an infinite value in both of these. So that means that L'Hopital's rule will apply. L'Hopital says that the limit as x approaches infinity of the original fraction equals the limit as x approaches infinity of the derivative of the top divided by the derivative of the bottom. Well, the natural log of x differentiates to 1 over x, and x differentiates to 1. So this is 1 over x, right? Now what does 1 over x do as x goes to infinity? Now we think about this, we say, well, how do we divide by infinity? Well, we're not really dividing by infinity. What we're doing is we're dividing by 10, then 100, then 1,000, then 10,000, then 100,000, then 1,000,000. And 1 divided by those values is always positive, but approaches 0. So that limit equals 0. Basically, whenever we have infinity on the denominator, we're going to get 0 as an answer. Unless, of course, it's infinity over infinity, and then we have to deal with L'Hopital's rule. So this should not be terribly surprising when we compare y equals the natural log of x to y equals x, which looks like that. They both grow, but this one grows faster. It grows linearly. Well, whereas the slope is always 1, whereas this one, the slope gets less and less and less as we go on. So the numerator is smaller, the denominator is bigger, so it shouldn't be terribly surprising that we get an answer of 0 here. Alrighty, this function, sine x over x, is extremely important to calculus. It should look familiar from back in chapter 1. We talked about it a bit in this class. We talked about how the squeeze theorem can be used to prove this. And that's a great proof. It's a foundational proof for all of trigonometry as it relates to calculus. But let's try a simpler method. If we ask the question, what is the limit as x approaches infinity of the numerator? we'll notice that it does equal the same thing as the limit as x approaches 0. Did I say infinity earlier? I meant 0. Of x, namely, it's 0, right? These are both continuous functions. We can just evaluate sine of x at 0. We can evaluate x at 0. We get 0 at both points. So because we get 0 over 0, remember those are the two magic values, right? Infinity or 0. If the top and the bottom are both 0, or if the top and the bottom are both infinity, then L'Hopital. I have to sing when I do L'Hopital's rule. I don't know why, it's just a thing. So we take the derivative of the numerator, we get sine of x differentiates to cosine of x differentiates to 1, and that becomes cosine of 0 over 1. Or just, well, I'll go ahead and write it out, cosine of 0, which equals 1. And again, that's something that we should remember from chapter 1. That was provable using the squeeze theorem. It is a lot faster to use L'Hopital's rule. Of course, back in chapter 1, we didn't know what derivatives were, so we couldn't use that method. So that's why we postponed the discussion until now.